All right, everybody, welcome to section 5.4, solving systems of equations with infinitely many solutions and no solutions. Up until this point, we have solved systems of equations that have had one solution, and we have found that one solution either by graphing, substitution, or elimination. So today I want to look at systems of equations that actually have either no solutions or more than one solution. So we have two examples here. And the directions are asking us to solve each of these systems of equations by graphing. So for example number 1, we have equation y equals negative 2x plus 2 and y equals negative 2x minus 2. So typically how I solve systems of equations by graphing, I take each equation and I will identify the y-intercept and the slope. And since both of these are already in slope-intercept form, I can go ahead and begin to identify those pieces of information. So for the first equation, y equals negative 2x plus 2, my y-intercept is going to be positive 2. My slope is going to be negative 2 over 1, which I should know is 2 down and 1 to the right. So I can go ahead and plot that. I have my y-intercept of positive 2 right here. I'm going down 2 to the right 1, down 2 to the right 1, down 2 to the right 1, all the way across my graph until I hit the edges, and also working it in reverse so I hit the edge in the opposite direction. Once I have all my points plotted, I'm just going to go ahead, connect all of those points. And that pink line there is the graph for the first equation. Moving on to my second equation, I have y equals negative 2x minus 2. My y-intercept here is negative 2, and my slope is negative 2 over 1, again telling me to go 2 down, 1 to the right. So I plot my y-intercept first at negative 2, and then follow my slope 2 down, 1 to the right, all the way until I hit the edges of my graph, working in both directions. Hold on. Actually, hold on, I made a little mistake right here. Let me erase these 3 points. Try again. There we go. Once I have all my points plotted, I can go ahead and connect them. And that blue line there is the graph of my second equation. So when we've solved systems by graphing in the past, we know that the solution is the point of intersection. Well, what happens here in example 1 is that I don't have any points of intersections. These lines are parallel. And since I don't have any intersections, I can say that the solution to this system is no solution. And again, that's because these two lines don't intersect. Before I even graphed these, I should have noticed that these were going to be parallel lines because I do have two equations with the same slope but different y-intercepts. So every single time that happens, I have two equations, same slope, different y-intercepts. I know the lines are going to be parallel, or I should know the lines are going to be parallel, and that in turn would tell me that there will be no solution to the system. So if you go through the work and you say, oh, hey, there is a solution, but you notice that they should be parallel, that's a sign that obviously something went wrong and you should be able to go back and double check what that mistake was. And that's it. That's it for example 1. Moving on to example 2, again, I have two equations. So starting with my first equation, I'm going to look at y equals negative 2x plus 2. Y-intercept is 2, slope negative 2 over 1. So just like in example 1, this means 2 down, 1 to the right. And so I can go ahead and I can graph that. I have my y-intercept at positive 2, and then I'm going 2 down, 1 to the right, all the way across my graph in both directions until I reach the edges of the graph. Once I have all my points plotted, connect all those points. And that pink line there is the graph for the first equation. When I move on to my second equation, the problem here is that I am not I don't have an equation that's written in slope-intercept form. So before I can start identifying y-intercept and slope, I have to try and get this to look like slope-intercept form. So I subtract 6 from both sides, so these cancel. On the left-hand side of the equal sign, I get 6x minus 6, and that's equal to negative 3y. I'm then going to divide both sides by negative 3. These will cancel. Let's see, over here, negative 6x over, positive 6x divided by negative 3 will give me a negative 2x. Negative 6x divided by negative 3 will give me a positive 2, and then I'm just left with the y on the right side. So I'm going to just rewrite this so it looks like y equals mx plus b, and I get y equals negative 2x plus 2. Now at this point, I should notice that the second equation and the first equation can now be written as the same thing, which means that the y-intercept and slope for this second equation will be the same as the first equation. So when I go to plot these points for the second equation, what I'm going to find is that this line for the second equation lies directly on top of my first line. As a matter of fact, it's the exact same line. So if my solutions are supposed to be points of intersection, then that means every single point on each of these two lines are points of intersection. So as opposed to having one solution or no solutions, for example 2, I'm working with an example that has infinitely many solutions. Now, when I work with examples like these on a graph, it's nice and easy because I can physically see that either there will be no points of intersection or there will be infinitely many points of intersection. But if I try to move on to substitution and elimination, I'm not going to get that visual image on the graph. So I have to know what happens algebraically when I start to work through these problems. And that's exactly what this next page is here. This next page is here. So example 1 and example 2 here are the same exact examples from the first page, except this time the directions tell me to use substitution for number 1 and elimination for number 2. So if I work here with number 1, substitution, okay, I have something solved for y equals negative 2x plus 2 and y equals negative 2x minus 2. Since these are both set equal to y, what I'm going to do is set these two equations equal to each other. Or in other words, I'm replacing, one of the y's with, I'm really replacing this y with this negative 2x plus 2 right here. So now that I've set them equal to each other, I want to begin to combine like terms. So I'll start by subtracting 2 from each side. And I'm left with negative 2x equals negative 2x minus 4. I want to try to get my x terms together, so I'm going to add 2x to both sides. But look what happens here. Negative 2x plus 2x cancels. Negative 2x plus 2x cancels. So on the left-hand side, I'm left with 0, and that's equal to negative 4. My variables completely go away, and I'm left with this, 0 equals negative 4, which is an untrue statement. Now, based off of the graph of these systems of equations in example 1, I see that the answer to the system is no solution. So what that tells me is that when I have an untrue statement, that means I have no solution to this system. With example 2, first, I need to get my x's and my y's on the same side. So starting with y equals negative 2x plus 2, I'm going to add 2x to both sides. That leaves me with 2x plus y equals 2. For my second equation, I have 6x equals 6 minus 3y. I'm going to add 3y to both sides. That leaves me with 6x plus 3y equals 6. I'm going to stack these two equations on top of each other. And remember, during elimination, I'm looking for a variable that has same coefficient, opposite signs. I don't have that here, so I'm going to put parentheses around my equations. I'm going to flip my first two coefficients, and then I'm going to change the sign of the first. And then I will distribute these out to their corresponding equations, like so. And that leaves me with negative 12x minus 6y equals negative 12, and positive 12x plus 6y equals 12. From here, I want to go ahead and add my equations together, but look what happens when I add the equations. Negative 12x plus 12x cancels. Negative 6y plus 6y cancels. Negative 12 plus 12 cancels. So everything canceled. My variables are gone, my constants are gone, everything has canceled. And if I look at example 2 in the graphing part, I know that this is supposed to have infinitely many solutions. So that tells me that when I do things algebraically and I get to everything canceled, what that really means is infinitely many solutions to the system. Okay, so graphically, again, it's a little bit easier. I know what the graphs are supposed to look like to have infinitely many or no solutions. Algebraically, anytime that I get an untrue statement, okay, that means my answer is going to be no solution. Anytime everything cancels, that means I'm going to have infinitely many solutions. So just to recap that here, a system of equations with no solutions, okay, graphically, two parallel lines that never intersect. And again, we can identify that by same slope, different y-intercepts. Algebraically, I know that once I start working on the problem, if my answer is no solutions, I will end up with some type of untrue statement. So for example, that 0 equals negative 4. For infinitely many solutions, graphically, I have two lines that lay right on top of each other. In other words, they're the same line. And we can identify that by really same slope and also same y-intercept. Okay, but algebraically, everything will cancel here. Unlike, no solutions where I get untrue statements. For infinitely many solutions, everything is going to cancel. Just please be aware, my final answer for these problems are not untrue statement or everything cancels. I know I wrote that, here in the example problems, but just recognize I'm writing that because it tells me what my final answer is. So anytime I get an untrue statement, that means to me no solution. Anytime everything cancels, that means to me infinitely many solutions. Okay, so I would hold on to this. This is going to be really useful, especially while you're still getting used to it so that you can remember. But the way that we do these problems are the same as we've always done them. It's just the result that changes here. Okay, so please let me know if you have any questions. Bring this note packet in tomorrow, and don't forget to do your Google Forms. See you later.